We are now on the last unit of Physics 30, and the last unit is called Atomic Physics, and it's really all about the nucleus. The nucleus. So in the previous unit, in EMR, and the last part of EMR, which is intermingled with atomic physics, we discussed the nature of the atom, going from the plum pudding model to Rutherford's model to the Bohr model, and then beyond that, we got the Schrodinger model and so on. Now we're just going to talk about, and that really involved the electrons and how they're related to the atom. Now we're going to talk about the nucleus. And there's a good video here called How Small is the Atom? If you go to YouTube and watch that, you will probably enjoy that to appreciate how small atoms really are. And here we go, the nucleus. So the first term that you should know is this term, if you don't know it already, and it's nucleon. And the nucleon is the name given to anything that you find in the nucleus. So it's essentially protons and neutrons. A proton is a nucleon. A neutron is a nucleon. Anything that's in the nucleus is called a nucleon. Then we go through the symbols that we can use for protons and neutrons. P positive, because it has a positive charge, and that positive charge is the elementary charge. And we know that the elementary charge is 1.6 times 10 to the negative 19 coulombs. That's the charge of an electron. That's the charge of a proton. Just one is positive, one is negative. They cancel each other out to make it neutral if there's one of each. Then we have the mass of a proton right here, extremely small, but extremely big compared to the electron. Remember, this is the mass of an electron. So if you're just dealing with the exponents, negative 31, negative 27, that would be, if you subtract those, you get 10 to the exponent 4, which is 10,000. So just in very approximate numbers, a proton is 10,000 times more massive than an electron. And the proton, this is the important thing, the proton gives you the atomic number, and it has a symbol of Z. And the atomic number, or the number of protons, is what determines what the element is. So for example, if you have 8 protons, you are oxygen. No matter how many neutrons you have, no matter how many nucleons there are in total, if there are only 8 protons, 8 and exactly 8, you are oxygen. If you have 6, you are carbon. Moving on to neutrons. So there's a symbol for neutrons. You can see that the mass of the neutron is just a wee bit bigger than the mass of a proton. And there is a generally accepted answer to that, which we will go on to, we will discover later on in the unit. And the number of neutrons in the nucleus, the neutron number is N, and the total number of nucleons. Now, wait a minute, did I forget about the atomic mass here? Yep, right here. So the total number of nucleons, the number of protons and neutrons, is called the atomic mass number. So don't get the atomic number and the atomic mass number confused. And that's uses the symbol A. So if you want to find out what the atomic mass number is, you simply add the number of protons and the number of neutrons. And then this is the commonly accepted way of writing out elements, where X is the element, A is the number of nucleons, and Z is the number of protons. So if I have something like, oh, I should have brought my periodic table, and there isn't one here. That's okay. If I have something like 14, I don't even know what 14 is. X, let's do one that I know. I know carbon, 6, C, and then I put a 14 there. And the question is, how many protons are there? Well, that's obvious. The answer is there are 6 protons. How many nucleons are there? The answer is 14. To get how many neutrons, I would subtract. So 14 minus 6 equals 8. So there are 8 neutrons in carbon 14. And carbon 14 is used for radioactive dating. That's how we know the approximate ages of the dinosaurs and rocks on Earth, and why the Earth is approximately 4 to 5 billion years old. Okay, moving on. Oh, here we go. We got an example right here. A nucleus has 7 protons and 8 neutrons. Identify what element it is and write out the symbol. So if it has 7 protons, the 7 goes down here. And if it has 8 neutrons, what number goes up here? 15. Because 15 is the number of nucleons, the number of protons and neutrons combined. And then you look on your periodic table, and if you're writing a physics diploma or a physics test, you always get a periodic table with you, and you will find out that that is N for nitrogen. Now, what would we call that element? We would call that nitrogen 15. And if I said nitrogen 14, then that would just be a nitrogen atom that only has 7 neutrons instead of 8 neutrons. And if I said nitron 17, it would have 10 neutrons. But all the time they have 7 protons, because the number of protons determine what element it is. If you've got more protons, if you go to 8, so you've got oxygen. If the nucleus has a symbol 23Na, identify as much as you can about it. Well, first of all, we know that it has 23 nucleons. We know that it has 11 protons. Therefore, it has 23 minus 11, which is 12 neutrons. Anything else we can identify about that? Well, it's sodium. Na is sodium. So what will we call this element? We will call it sodium 23. Moving on to isotopes. What are isotopes? Isotopes are simply an element that has a different number of neutrons. The same element, but has a different number of neutrons. So here's some really good examples. We got carbon-12. Carbon-12 is the most abundant form of carbon on Earth. It has 12 nucleons, therefore it has 6 protons and 6 neutrons. There are other forms of carbon. We have carbon-11, carbon-13, carbon-14. Gives you the relative percentages or abundance. And as we said, carbon-14 is used for carbon dating, and so on. So an isotope is simply the same element that has a different number of neutrons. Remember, if it has a different number of protons, then it's not the same element. It's a different element. Onward. Now, you can read all this, but it's about the averages. It's not really important. Too important. This is important though. Atomic mass units. So atomic mass units, AMU, and we just use the symbol U, not mu, but just U. They're not part of the metric system, but we still use them. I don't know if they're going to eventually fade out into oblivion like astronomical units. But atomic mass units is simply because we know that the mass of one proton is no, not the mass of one proton. So let's read overall so you understand it, because it's I said this may fade out in years. It's just a way, because everything is really small, just like electron volts. Instead of using this number for electron volt, instead of just using this number for energy, we like to just say that this equals 1 electron volt, just because it's an easier number to use. Same with atomic mass units. Instead of having to use this number all the time, 1.660539 times 10 to the negative 27, we just say that that equals 1 atomic mass unit. And this is why this is kind of arbitrary, because an atomic mass unit is based on the neutral atom of carbon-12, which is given a mass of exactly 12 atomic mass units. So here are numbers, and these numbers are not given to you on your formula sheet. So their relative importance is questionable at best. But this is just a way of measuring masses of protons, neutrons, and electrons without having to write times 10 to the negative 27 or 10 times 10 to the negative 31 every time. Okay. Next important concept, binding energy. And this is the one that we'll, oh, we're at 10 minutes. We'll just discuss this. We'll split this lesson into two. And then we will, just because it's going to be very long. Binding energy. The binding energy, so this discusses, you've got protons and neutrons packed together in a nucleus. Protons, proton, proton, neutron, 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 neutron. And the question is, these protons are all positively charged. Why are they not? Why does the electrostatic force not just rip them apart? How are they staying together? One explanation would be, well, the gravitational force is keeping them together. But if you look at the next page, you see a comparison between the gravitational force and the electrostatic force, and there is no comparison. This is the gravitational force between two protons. That is the electrostatic force. As you can see, the electrostatic force wins by, it's not even close. It's not even remotely close. Negative 28, negative 64. So the electrostatic force should be breaking the nucleus apart. There must be something else keeping it together. And that's what we call, right here, the strong nuclear force. The strong nuclear force is what keeps the nucleus of an atom all together. The strong nuclear force. And it says the strong nuclear force can act over incredibly small distances measured in femtometers. The strong nuclear force is so short range that it can actually only attract other nucleons that are right next to each other. Nucleons that are on the opposite sides of the nucleus do not affect each other by the strong nuclear force. And that is why, I'm just going to go, that is why the bigger an atom gets, the more unstable it often gets. So if you have most basic atom, which is, that's a hydrogen atom. Hydrogen atom, that's very stable. Hydrogen is very stable. As soon as you start adding neutrons and protons, okay, so now we have, what do we have now? Excluding the electrons, forget about electrons. Now all of a sudden we have a helium atom, 2 protons and 2 neutrons. Right? And the strong nuclear force keeps these together because they're right next to each other, no problem. But when you're getting up to really big elements that have, for example, let's say, what is it? Uranium. I think uranium is 92. Uranium has 92 protons in it. And of course, I'm not going to draw 92 protons. Some are going to be really far away. And they are not affected by the strong nuclear force. And therefore, those elements tend to be less stable. In other words, they can, some of these protons or some of these neutrons may be ejected from the nucleus, which is called radioactive decay. And it also is what's responsible for fission and nuclear bombs and nuclear power plants and so on. Okay, so that's, let's go back up and finish binding energy, or just finish the straw. That's the strong nuclear force. So we'll stop there and we'll go on to the second part of this lesson.